To evaluate these integrals in spherical coordinates, we need to do a few transformations on the equations, on the limits of integration. Again, many of these integrals that we would be given in Word, so number one, or already as a set of integral in rectangular form, we're not going to be able to evaluate. So we would need to really transform this integral to spherical or potentially cylindrical. Well, how are they going to look like? Well, number one, so let's talk about the differential. The differential dv, right? Because we integrate a solid, that means we integrate over some dv. So we will turn that dv into rho squared sine phi d rho d phi d theta. In a similar way, dA became, what was that? R d theta in polar, and dv in cylindrical became r dz d r d theta. We just added dc. Well, here for spherical coordinates, it's going to be a little bit more complex. Okay. Now, if the integral, this triple integral may or may not represent the volume as usual, as we did back in cylindrical, for instance. If this f of x, y, z, it's just a 1 for sure, that triple integral is for volume. Otherwise, if it's not just a 1, if it's something else, well, that will represent something else. So here, x will be replaced with rho sine phi cosine theta using the relations y, rho sine phi, sine theta, and lastly, z, rho cosine theta. What about the limits of integration? Well, so the innermost limits of integration, which are rho 1, rho 2. Okay, so this rho, which is the radius of the sphere, well, that's in the case where we're integrating over a very simple sphere. However, what if the solid is not a sphere, for instance? What if it's bounded above by a plane or maybe by a cone? Well, those rho's are going to be expressed in terms of those equations that describe those solids. So that means we have 3 or 4 case scenarios. Those rho's may be just constants. Number 2 could be functions of phi and theta. Number 3, just a function of phi, or number 4, just a function of theta. The second limits of integration, phi, the drop-down angle, can be simple constants like 45 degrees, 30 degrees, or pi over 4, pi over 6, etc. Or can be functions of the outermost limits of integration, which is theta. We'll see a few examples of each. And lastly, the outermost integral will have limits theta 1 to theta 2, which are going to be the polar angles, and those are simply constants. There's no way around this. Yes.
Isn't the cosine of phi not theta?
Cosine of. Oh yes, you're right. This is supposed to be phi right here. So a little typo I need to change. This one right here, right? By the way, the symbol phi, you may see it as either like this or sometimes like that. Depending on the textbook you use. Actually, the physics use this one, I think. It looks like I mean, that's phi, right? It's another way. All right, okay. So, where it's all coming from anyway? I mean, everything started in Calculus 1 when you found the area under the curve by partitioning the area into a few rectangles, adding the area of those rectangles to get the approximate area, but then you decrease that value of delta x to make those infinitely many rectangles, right? Then get the actual area. In a similar way, we did square regions to get the area between two curves using double integrals. And then we did the same with rectangular prisms for volume using a triple integral. For the integral in polar coordinates, remember that little slice of pizza, New York style pizza, and then the Chicago style pizza for cylindrical. But what are we going to do for spherical coordinates? Because it's still a solid, we will integrate over some rectangular box, over some box, right? But how is that box going to look like? That box, it's a partition of a sphere. Okay, it's on the next page. All right. So let's consider this sphere and take one piece of this of a box. All right. So that means, I mean, in general, how do we get the volume of this partition here? Isn't that simply length? Oh. Okay, in general, I mean length times width times the height. Isn't that volume? Isn't that just the volume? But well, because this box, do you see how it's twisted? It's not rectangular. I cannot just do length times width times height. So because it's circular on some edges, and yes, it's straight on one edge. Well, we need to consider all the different possibilities here. Okay, so that's why we have these additional curves to say help us get the or describe those differentials. Okay, let's start with the following. Okay, again, in general, volume equals length times width times the height. So in this case, we want to find the delta V, the delta for the volume. That's for the partition that will add infinitely many of those. Okay, that is delta V equals delta L, delta W, and delta H. Okay. Now, how do we describe each of the deltas? Okay, the delta L. Let me change colors first of all. So let's talk about three deltas here: the delta out, the delta around, and the delta up. What is that? What is each of them? So number one, delta out, delta around, and delta up. Okay, so out of where, around what, up to where. Okay, so let's describe each part. Okay, so that's why I have this imposed space, coordinate space. That is, this is the origin, and from the origin all the way along this straight line, that's going to be our radius of the sphere. So, and this will describe our delta out. So that is out of the sphere, from the origin out to your favorite radius. Okay? So, this will be row 1 to row 2. All right? Okay, let's describe each of the deltas separately. So number 1, the delta out will be simply row 2 minus row 1, right? That's all it is. Row 2 minus row 1, which is delta row. That's where the D row will come up later. That's it. As easy as that, right? Okay, so that's part A. Now part B. Part B, what about the delta around? So, around what? Okay, so that's going to be our delta around from the angle theta 1 to theta 2. Okay? That, if you look at the perspective, doesn't that look like the what's it called? The polar angle, the angle that goes around the sphere. Okay. So, but hold on, this cannot be just theta 2 minus theta 1 and just call it a delta theta. There's a little bit more than just this, because what are we describing when I go from theta 1 to theta 2? Isn't that a distance? Because we're multiplying the distance in length times width times the height. And well, the difference between two angles doesn't give me a distance. Hopefully you guys agree with me that this is some arc length, right? Does that look like an arc length? Well, so in this case, arc length. Okay, let me do that on the side. So S equals to r theta. That's going to be our this is going to be our length S, r theta. But well, in this case, we can use the letter r. That's because see this projection. It's a circular projection. It's not the sphere. It's just a circular projection onto the xy plane. So I'm just going to write the following: r times theta 2 minus theta 1, which is the same as saying r times delta theta. That's how we use the delta symbol to describe a terminal minus initial, or a final, or a 2 minus 1, you know. However, in our spherical coordinate system, we don't use the lowercase r. So we need to write that r in terms of rho, that is the radius of the sphere. Then for this, let me go back to the derivation for the coordinates. Remember how we express r in terms of rho and phi? So I'm going to use this relation, and that'll be rho sine phi delta theta. That's part B. Lastly, for part C, that is the delta up. Okay? Alright, that is from this point to that point. That is this length. But how do we describe that length? You might wonder. So, isn't that another arc length? But it's an arc length that it's going up, not going around. Well, how do we describe that arc length going up? Well, so number one, again, let's describe these angles right here. So this ray right here, let me call this phi 2 and phi 1. I know, because we're going up, technically we're going down as a drop down angle, so that should be 2 minus 1 or 1 minus 2. It doesn't matter. In the end, it's going to add up to a positive result anyway. Okay, so, but again, how do we describe this arc length? Well, in this case, if we were to use the formula for arc length in a similar way that we did over here, in this case, the radius, did you see how the radius right here from the origin to this point, it's the same as the radius from the origin to that point? And it's exactly the same as the radius of the sphere, right? That's why I'm not going to use a lowercase r. I'm going to go straight up to rho, and then that's phi 2 minus phi 1, which is the same, what's that? It's the same as rho times delta phi. Now, coming back and putting everything together, finally, delta v, which is delta out, that is simply delta rho, times delta around, which is rho sine phi delta theta, and times finally the delta up, which is rho, what's that? I think I'm missing. Am I missing anything? I think I'm missing a factor of rho. No, never mind. Rho delta phi. All right. Putting all this together, what is that? Delta v equals to rho times rho. Isn't that the rho squared you see in the differential in the integral? And then sine phi delta rho delta phi delta theta. And this is where the differential comes from. Well, in this case, I'm doing this in terms of deltas. That's because it's a partition, a finite partition. However, if we slice the sphere into infinitely many of these twisted rectangles, add infinitely many of those deltas become these, right? By Riemann sums. Doesn't that match with what we have over here? Okay, let me go back. Yes, rho squared sine phi d rho d phi d theta. And that's where it comes from. It's a basic geometry. basic geometry idea behind putting together some ideas from trigonometry such as arc length and terminals minus initials, all about deltas. All right, how about we evaluate our first integral in spherical coordinates? Okay, let's go about our first example on the next page. Oh, it's in the same page actually. Okay. Convert the spherical coordinates, then evaluate all this. Okay, the integral from 0 to 3, from 0 to the square root of 9 minus x squared, and from 0 to 9 minus x squared minus y squared, of the integrand, which is the square root of x squared plus y squared plus c squared. Doesn't matter. What we care is the limit. Of course, I have a GeoGebra solid construction here, but let's think about where are we integrating over here. Okay, let's think about it. Okay, so we are integrating over 1/octant of a sphere. Okay, let's get more information about the sphere. Number one, is it going to be the upper hemisphere or the lower hemisphere?
Upper.
How do we know it's the upper?
We have like 0 as a lower bound.
Uh-huh.
All the values have to be positive.
Okay, so 0, that means the floor, it's the xy plane, and the upper radical means upper hemisphere, right? Okay. Upper hemisphere of radius. What's the radius of the sphere, by the way? What's the radius? Someone else. What seems to be the radius of the sphere? 1. It's a unit sphere. 3, okay? That's because we have the integral from 0 to 3. Because we have this 9. Because we have this other 9. Okay, the inner limit of integration, square root of 9 minus x squared. What does that represent? So now let's forget about 3D. Now we're going to D, right? We're going to dimensions.
A semicircle.
It's a semicircle. Well, let's call it, semicircle. Is that the upper or the lower?
Upper.
The upper. All right. Okay, lastly, that's 0 to 3. What does that tell us? That's 0 to 3. Someone on this side. Okay. What does that 0 to 3 tell us about? So yes, we have a hemisphere that projects a circle, of course, onto the xy plane.
Maybe the length.
Yes, the length.
Is it because we have like the intercept, we have like the symmeter, upper symmeter,
Yes.
upper symmetrical. So you got like the cylinder, like one type cylinder, they go like lengthwise.
It's not a cylinder in this case. We're still okay with
No,
with
it's
the.
like cylinder, pues kind of cylinder, pues una like have like
Mhm.
reach.
Yeah. So it has to do with the length for sure. Well, this 0 to 3. What tells us about this upper semicircle?
We integrating from like half of it because we go from -3 to 3, but now we're just going from 0 to 3.
So it's only the first quadrant, right? A quarter of a circle, right? So, okay, let's plot that onto the xy plane. So that is the upper semicircle, but only the part that goes between 0 and 3, okay? So, get its shade. All right. Well, that's going to help us for sure get the limits of integration for the radius only. Well, no, not for the radius, for the polar angle, which is going to go simply from 0 to pi over 2. Now, let's have a look at the solid. I know I have the file right here. So there you go. Okay. Triple spherical example 1. It didn't go through. All right. There we go. So this is our solid right here in question. So let me, if we were to have all the sphere, which I have it overlapping the solid, well, let me uncheck the entire sphere. So really, we have indeed that projection onto the xy plane of the sphere, which is just a quarter of a circle. Which in this case, well, let's put the solid perspective. That's just 1/8 of the volume of the sphere. I mean, um, looking at the solid will help us now get the remaining limits. Number one, what is the radius of this sphere? This radius of the sphere seems to be 3 at all times because it's a sphere. The radius seems to be constant. Good. Okay. Number two, what about the drop down angle, that azimuthal angle? So again, we're going to start from the North Pole, and we're going to walk all the way to, not all the way to the South Pole, right? Just as far as the equator, right? So what's the angle from the North Pole to the equator? Pi over 2, all right? So we're ready to write this integral in spherical coordinates. Let's go back to the notes. And, okay, so, domain of integration, of course, that's going to be rho phi theta, such that, well, I mean, the domain in rectangular, we don't need it. So rho varies between 0 and 3, and phi varies between, 0 and pi over 2. And lastly, the angle theta, the polar angle, varies between also 0 and pi over 2. All right? So yeah, guys, you don't want to value that triple integral that we're given. This is the power of spherical coordinates. Check this out. The integral from 0 to pi over 2. The integral from 0 to another pi over 2. And the integral from 0 to 3. Okay, hold on. What is x squared plus y squared plus z squared in spherical coordinates equal to?
Rho squared.
Rho squared. Okay, rho squared. That's the square root of rho squared. What does dz dy dx become from rectangular to spherical? Isn't that rho squared sine phi d rho d phi d theta? Look at that integral. Isn't that way easier to evaluate? Not even variables on the limits of integration. It's all nice and easy numbers, constants. All we need to worry about is simplifying that integrand. I mean, come on. The square root of rho squared is rho. Times that rho squared, isn't that rho cubed? The integral 0 to pi over 2, 0 to pi over 2, 0 to 3, and that's rho cubed sine phi d rho d phi d theta. Okay, integrating with respect to rho, that'll give us 1/4. I'm going to write it outside. 0 pi over 2, 0 pi over 2. That's rho to the 4th from 0 to 3. Sine phi d theta. Upper limit minus lower limit, 3 to the 4th power, 81. Well, let me do the 3 over to the 4th power. That's 1/4. Integral from 0 to pi over 2. From 0 to pi over 2. That is 3 to the 4th minus 0 to the 4th. Sine phi d theta. 3 to the 4th, that's 81, right? I'm going to write that 81 outside multiplying with the 1/4. That'll be 81/4. New 1/4 integral from 0 to pi halves. Another 0 to pi halves. Sine phi d theta. Now, how do we know we're doing good so far? Because, well, now we're going to integrate with respect phi. We have our d phi, and the outermost limits of integration are the theta, which is the polar angle. So let's integrate with respect the azimuthal angle, that is phi. And the integral of sine, careful, that's negative. Cosine, that's negative 81/4. Integral from 0 to pi over 2. Cosine phi, evaluated between 0 and pi over 2. D theta. Upper limit, okay, keep the negative 81/4. Okay, that is the integral from 0 to pi over 2. Cosine pi over 2 minus cosine 0. What is cosine pi over 2? 0. Cosine 0 is 1. 0 minus 1, isn't that negative 1? That equals negative 81/4. Integral from 0 to pi over 2 times negative 1. Negative 1 d theta. Oh, negative times a negative, positive. That's 81/4. Integral from 0 to pi over 2 of d theta. And come on, this integral, is that just equal to theta, 81/4? Theta from 0 to pi halves. And that equals 81/4 times pi over 2 minus 0, which equals 81 pi over 8 units. Yeah, this is a lot better than attempting the original integral. I think it could be potentially doable. You would have to set up trigonometric substitution with 3 variables. I don't think it's the most impossible task in the world, but it's just going to take forever. It's not going to be the most practical thing in the world to do. Anyway, let's have a look at another example. Okay, and we did one similar to this. Did we? Yeah, we did. Okay. Use spherical coordinates to write a triple integral. We're not going to evaluate, just set up that represents the volume of the solid region bounded below by the cone and above by the hemisphere. Z equals to 16 minus x squared minus y squared. Didn't we do something like this back when we first learned about triple integrals? We had that ice cream cone. Well, I believe we had a different sphere. We had the sphere, instead of a 16, it was a 40, I think. But the shape is going to be very, very similar. This setup will be also similar. All right. So, number 1. So, okay, without GeoGebra, because we need to see the projection of this solid onto the XY plane. Number 1, what do we do? If every time you're given only one surface, just set z equal to 0 and get the equation of the conic, whatever that is, and graph it. But in this case, we're getting 2 surfaces. What do? Set the 2 equations to get equal to one another. That is, set this radical equal to that other radical. That is, square root of x squared plus y squared equals to the square root of 16 minus x squared minus y squared. All right, let's square both sides, get rid of the radicals. That is, x squared plus y squared equals to 16 minus x squared minus y squared. And move all variable terms to the left, keep the constant terms on the right. That'll be 2x squared plus 2y squared equals to 16. And dividing both sides by 2, we get x squared plus y squared equals to 8. What is that? X squared plus y squared equals to 8. What does that represent?
Circle of radius 2 and 2.
Circle of radius 2, radical 2, or root of 8 centered at the origin, which should make sense, because think about it, without even looking at GeoGebra yet, we will in a second. Without looking at GeoGebra, think of a cone and the ice cream at the top. Don't they intersect forming a circle? And then that circle, boom, slam it onto the xy plane. That's going to be the same circle. X squared plus y squared equals to 8, which is root of 8. Okay, so let me plot this circle real quick. So that is circle of negative root of 8 root of 8, negative root of 8, root of 8. And no, you don't even want to set up a triple integral in rectangular. We're going to go straight to set an integral in spherical. Okay? All right. What else should we do here? Okay, number 1. This will be our sphere. Z squared equals to 16 minus x squared minus y squared. So x squared plus y squared plus z squared equals 16. Okay, what can you tell about that equation? X squared plus y squared plus z squared equals 16. What is that?
Row?
Well, it's rho. Okay, rho squared. First of all, rho squared equals to 16, right? But I mean, geometrically, what is this? X squared plus y squared plus z squared. What is that? Sphere of radius 4, right? Sphere of radius 4, okay? So that's what's on the top of the cone, right? The sphere of radius 4. Okay, then we need to describe this cone in what was that? In spherical. Remember we had z equals square root x squared plus y squared. I left some space on purpose because I need to write these invisible ones, right? Remember we had a way to describe the equation of a cone in spherical with the relation, what was that? Phi equals arctangent of the square root of 1 over the square root of a. But in this case, a equals 1 arctan of 1 over the square root of 1, which is pi over 4. I mean, I think for this one it's obvious, right? So, but I mean, we still need to write it algebraically, especially for the next set of problems. All right, so is there anything else we can get algebraically? I wonder if this is enough to set up a triple integral in spherical already. What do you think? Do we need the solid in the algebra at this point? Let's have a look at it. Okay, let's have a look at it. So, that is the solid over we're integrating over. Okay, so that'll be, make this bigger. Okay, so that's x, y. All right, what about the projection? Number 1, the 2D projection. Isn't that the circle we just did by hand? Right? So do you see this, what's it called? This curve right here? You see, yes, right here. That's the curve, the intersection curve we got algebraically, which gets projected onto the xy plane here. And it's shaded accordingly just so we can see what's the region of integration in the xy plane, of course. All right, now let's talk about the solid, because in this case we're no longer go roof minus floor and then the xy. It's now drop down angle or azimuthal angle. What else? Polar angle and the radius rho. So let's talk about rho. So number 1. If we think about it, what's the distance between the origin and any point? Do you agree that this distance is always the same? It's 3 units. So it's changed. Well, it's constant in accordance with the equation of the sphere given by x squared plus y squared plus z squared equals to, what was that? 16, right? That's 4. So the radius is going to go from 0 all the way to 4. All right. So I think we can write that part of the integral. So a volume, which is the triple integral over the region R, dv, that is the integral that goes between, that is rho squared sine phi d rho d phi the theta. So for the radius, it's 0 to 4. Okay, what about the phi angle? That is the azimuthal angle or the drop down angle. Okay, so again, we will always start at the North Pole. So we're gonna walk from the North Pole and see if we can make it all the way down to 180 degrees, which is the South Pole. But it turns out, hey, if we start at the North Pole, okay, better perspective. And where are we going to stop? I didn't click on animation anyway. So are we not going to stop at 45 degrees or pi over 4? Okay, so that's going to be our upper limit for the drop down angle, 0 to pi over 4. And lastly, what about the polar angle? Here is where we look at the what's it called? The projection onto the xy plane, which isn't that 0 to 2 pi? 0 to 2 pi, all right? That's all it is. 0 to 2 pi, all right? But in this case, they're only asking us to set up the triple integral. And by the way, let's write the domain of integration in set notation. That is, the domain D will be rho phi theta equal to, what's that? Oh, no, wait, such that rho varies between 0 and 4, phi varies between 0 and pi over 4 or 45 degrees, and lastly, theta varies between 0 and 2 pi. All right? Okay, how do we know it's 0 to 2 pi? Because there's no additional condition. So when they tell us, okay, the volume bounded by these two surfaces, that's it. It is safe to assume that it's the entire solid, unless they say, oh, use spherical coordinates to write a triple integral that represents the volume of the region R, blah blah blah, in the first octant. If it said in the first octant, then our limits for the polar angle would have been 0 to pi over 2, because that's only the first octant. Okay? So that's our result. In this case, we just want to set up the triple integral. Okay? All right. Let's have a look at another exercise, another setup problem. Set up a triple integral in spherical coordinates to find the volume of the solid bounded by two cones, given their equations, and the plane at the top, z equals to 3. Okay. All right, so let me open the solid for this. I'm going to start with the solid first. Okay, so that's 16. Okay, there you go. So that's the solid we're talking about. Let's describe. So notice how we have a cone inside a skinny cone inside a wider cone, and it's bounded above by a plane. Yes, of course, that plane it's already trimmed with these circles that describe the solid. So we need to set up the integral that calculates the volume for this. Okay. So of course the xy projection. Well, it's in this case. Well, let's look at this perspective first of all, and see. Is the radius constant? Is the rho going to be constant this time? That is the distance from the origin to this point the same distance as the origin to that point or to that point? That doesn't seem to be the case, right? Because in this case, we're no longer integrating over a sphere. We are integrating over a roof that's not spherical, it's a plane. So that's going to change the distances between the origin and any point on the plane. All right, what else? So we have in this case two cones that we will represent as phis in this case, all right? So we have an equation, we have a relation to express those equations, right? And then that's just going to be our drop-down angle, all right? And then, of course, the xy projection. What do you think the xy projection is going to be in this case? The limits of integration. Again, 0 to 2 pi, because it's the entire rotation. All right, now we have a bunch of stuff to do for this one. Okay, so let me go back to the notes. Number one, I would like to draw the region of integration onto the xy plane, but I would need to get these two equations algebraically first of all. All right, so okay. That is this circle and that other circle. All right, these two circles. Hey, what happened here? That's one circle and that's another circle. I need to get the equations of those two circles. So how do we get them? I need to get simultaneously this equation, the first radical equals to 3, and then the second radical also equals to 3 to get those two equations. Well, that is 3, or rather radical square root of 9x squared plus 9y squared equals to 3, and square root of x squared plus y squared equals to 3. Squaring both sides, that's going to give us the following. 9x squared plus 9y squared equals to 9. That is the equation x squared plus y squared equals to 9. Isn't that the equation of a circle of radius 3, center at the origin? Well, my centers over there do not look perfectly at the origin, but I mean, you get the picture. Square both sides here. That is, oh, hold on. That should be equal to 1. It's the unit circle. That's a unit circle. I was looking ahead at the next one actually. X squared plus y squared equals to 9. All right? So that's how we get the other projection. Unit circle, circle of radius 3. And the angle theta, we can already see it's going to be between 0 and 2 pi. Pretty easy because it's the entire region. They're not telling us the first octant or the first two octants. No, they don't say anything. It's the entire region. All right. And what else can we do about it? Okay, get something real quick. Okay. Let's represent the equations of these cones as drop-down angles. Okay, number one. Z equals to the square root of, what's that? 9x squared plus 9y squared, and z equals to the square root of x squared plus y squared. Okay, what is a in this case? Do you guys agree a equals to 9? And over here a equals to 1. That is the number multiplies the squared variables. So phi, that's going to be arctan of 1 over the square root of a, which is arctan of 1 over the square root of 9, which is arctan of 1/3. Oh, the question here is 1/3 one of the tangent values of a special angle? Yes. No, it's not. Just leave it in terms of arctan 1/3. Arctan of 1/3. Okay. What about here? Phi equals to the drop-down angle. Okay, arctan. 1 over the square root of 1. Come on, we did it. We did this one a few times already. I think it's clear this is pi over 4. All right. Let me go back to the solid. Okay, number one, can someone help me get arctangent of 1/3 in radian mode, please? Or you know what, in degree mode is fine. Degree mode is fine. You should get an angle that is, what's that, smaller than 45 degrees for sure. 18.4, right? 18.4 degrees and 45 degrees, exactly. Okay, does that look, okay, this perspective. The inner cone, the drop down angle, does that look like, I mean, compared to the green cone, which clearly is 45 degrees, does the angle for the first cone look like 18.4 degrees? Makes sense, right? Looks like it is. Okay, so what's next? I think we're ready to evaluate. Oh, wait. The radius. We need to establish the radius because, well, clearly the smallest radius is 0, right? It's gonna start from the origin, and the radius will vary. It's not going to be constant like 5, rho equals 5, rho equals 7, depending on the sphere, because it's not a sphere. Again, the distance from the origin to this point, it's different to that point and to that point. So we need to express that rho in terms of uh, rho, phi, and theta. If we had a sphere, for instance, we just would have said rho equals 5 for a sphere of radius 5. If we had a sphere of radius, say 7, just rho equals 7. But in this case, it's not a sphere. What is the shape at the top of these two cones? Or what is the surface that describes the top of the cones? Isn't that a plane? Remember how we wrote equations of planes before getting into the integrals? Okay, so what is the plane? Is the plane z equals to 3? Okay, so we need to express z equals to 3 in spherical coordinates. What is z equals to? Isn't that rho cosine phi equals to 3? All right, and then rho equals to 3 over cosine phi, which is equal to 3 secant phi. And I believe we have everything we need to set up the triple integral that calculates the volume bounded between or inside between the two cones and bounded above by the plane, by the horizontal. I don't want to say horizontal because in space it doesn't make sense. Okay, so alrighty, so volume equals the triple integral over the region Q. By the way, let's write down the region of integration first. Q equals all the order triples. What's that? Rho phi theta, such that number one, oh, careful because rho varies between 0 and bounded above by the plane 3 secant phi. Phi varies. Oh, careful. What's going to be the lower bound for phi, by the way? The pi over 4 or the arctan of 1/3? That's why I asked you guys to compute it in degree mode so you can easily see which one is the smallest, because if I just look at these two numbers, pi over 4 and arctangent of 1/3, it's not clear to me which number is the smallest of them, all right? So, and I'm going to need more space here. Okay? So that is bounded below by arctangent of 1/3. What else? Phi, that's phi, and pi over 4. And lastly, it will vary for theta between 0 and 2 pi. All right, let's write down the integral finally. dv, that equals the integral. Okay, so that's the integral from 0 to 2 pi. That's the outermost limit of integration for which is the polar angle. The middle limit of integration, which describes the azimuthal angle, and in this case those azimuthal angles vary between arctan of 1/3 and pi over 4, and the third integral, which lower limit, that's for the radius of the spherical region. But again, it's not a sphere. The radius varies by the plane, not by a, not it's not constant by a sphere. So that is secant phi rho squared sine phi d rho d phi d theta. Fine.
What's the upper bound? 3 secant?
Oh, 3 secant theta. Thank you. Thank you. 3 secant theta. I mean 3 secant phi. 3 secant phi. Well, the purpose of this exercise right here is because the take-home quiz you're going to take today involves one situation like this, where you have two cones and a plane. I just helped you with the setup. You will be given one with different numbers. But in this case, you guys are going to have a lot of fun evaluating these integrals. It's going to look scary at first, but trust me, guys, this integral like this will simplify really, really nicely. It's so beautifully. All right. Okay. Before ending today, well,